This video is a walkthrough for combining the electric field strength of multiple charge questions. By the end of this video, you should have picked up the following skills in order to solve these kind of problems. You should be able to draw vector arrows indicating electric field strength at a point with the correct direction and magnitude. You should be able to break electric field vectors into components. You should be able to correctly combine electric field vector components to find the electric field strength's magnitude and direction. Alright, let's get started. In this question, we're asked to find the electric field strength at point P, which, as seen here, is in between charges Q1, Q2, and Q3. The electric field strengths are a vector, so we're going to have to add together the vector components in order to find the electric field strength at point P. The first thing we need to do to get started on this problem is to draw our vector arrows for each charge. We're going to think about each charge separately, and we're going to draw roughly the magnitude and the direction of each charge. So if I were to start with charge Q1, I'm going to change to red because it's indicated in red here. I have a positive point charge plus 2 coulombs. And remember that we define our point in our electric field as a positive test charge. So that means if I have a positive point charge and a positive test charge, it's going to repel. And so the red charge, Q1, would push point, if I were to put a test charge at point P, it'd push it to the bottom right-hand side of the screen. And that's going to be my electric field from charge 1. My electric field for charge 2 is going to be similar. So we see that it's another positive another positive charge, and it's going to push our positive test charge at point P to the bottom left-hand side of the screen. So that's going to be the electric field direction and magnitude for charge 2. Notice that I've drawn these arrows in the same length. That's because both Q1 and Q2 are positive 2 coulombs. That means they would have the same magnitude, but they'll have a different direction based on their different locations. We see that the last charge, Q3, is negative 2 coulombs. Okay, so we have a negative charge and a positive test charge. It's going to attract the positive test charge, so it's going to pull it down toward the bottom of the screen, toward itself. Okay, and this arrow should be roughly the same length as E1 and E2, because, once again, it's the same magnitude of charge and the same distance from the test charge. Now remember at the beginning of the video I said that electric field strength is a vector. So in order to add together E1 and E2, which are at angles and not in the same direction as E3, we're going to have to break these vectors down into their components. So I'm going to start with E1, and I'm going to use dotted lines to indicate the vector components. So E1 would have an x vector component to the right, like this, and a y vector component straight down, like this. So I'll call that E1x, and I'll call the y vector component E2x, or E2y. Oh, sorry. I can do the same thing for my E2 vector. So E2 would have an x component to the left and a y component straight down. Notice my E2x and my E2y, or my E2x and my E1x have the same magnitude but opposite directions. So that indicates that both of these vector components are going to cancel out each other and won't be needed to, and do not need to be included in the final calculation. We see that E2y and E1y and E2y are both, sorry, this should be a 1. E2y and E1y are both pointing downward, as is E3. That indicates that our final vector will have the direction, our final resultant vector will have the direction of toward the bottom of the screen. I'm going to clean this up so we can see things a little bit better. So now that I've cleaned it up, I'd like to find the y vector component of charge 2. And so I can see, because this is 30 degrees here, and this is a vertical angle to that angle. You can see this is also going to be 30 degrees. And so I can use my trigonometric properties and find the magnitude of the y component of E2. So we derive the equation electric field strength is equal to Coulomb's constant times charge divided by r squared in a different video and earlier on in the playlist. And we're going to use this equation to find the magnitude of the y component. Because this is the angle opposite my angle, because this side of the triangle here is opposite my 30 degree angle, I'm going to use the sine 30 degrees property to find E2y. Okay, so I need to do some substitution. E2y is equal to Coulomb's constant, 8.9 times 10 to the 9, times a charge of 2 coulombs divided by the distance, which is 3 meters to the point, squared, times the sine of 30 degrees. Okay, drop this in the calculator, and I find that the y component of the E2 charge at point P is 2.2475 times 10 to the 9 newtons per coulomb. So we'll express electric field strength as newtons per coulomb. In some situations you might also see volts per meter, but in this situation newtons per coulomb makes a lot more sense. So since charge number 1 is also at a 30 degree angle to the horizontal, I'm going to need to do something similar to find its y component. So draw it out. Okay, and since it's at a 30 degree angle, I can use this exact same calculation to find the angle, or to find the y component of E1, or the E1 electric field. So I do my substitution, and I get that the magnitude of the E1y vector component is 2.2475 times 10 to the 9 newtons per coulomb. Okay, so this E2y and this E1y are the magnitudes of those vector components, and if we look, we see that each vector component points straight down toward the bottom of the screen. So in order for my vectors to have magnitude and direction, I need to add a direction, and I'm going to do that by adding a minus sign to each of these vectors components. So that indicates that the electric field strength is pointed toward the bottom of the screen, not that the electric field itself is actually negative. Okay, and we'll work out the direction at the end of the problem. Last thing we need to do is find the magnitude of charge Q3 at point P. So remember we said before that it's pointing down toward the bottom of the screen, just like our y components of our other vectors. And it doesn't have any x or y components, so we're not going to need to use sine or cosine to find the components. It's just straight up calculation. So I'll use the equation we derived earlier, do my substitution, and I get 4.495 times 10 to the 9 newtons per coulomb is the magnitude of my electric field from charge 3. Okay, notice that it was pulling it toward the bottom of the screen, so it's going to have a negative here. Okay, so we found, at this point, we found all of the magnitudes of each charge at point P. Now we need to combine these. And so we'll just add together E1y plus E2y plus E3. I'm going to make a little room, and I get negative 9 times 10 to the minus 9 newtons per coulomb. Okay? Now, electric field strength is never negative. Okay? So this minus sign here doesn't indicate that I have a negative electric field. It just indicates that I have a direction to my electric field that is toward the bottom of the screen. So what I'm going to do is I'm going to erase that minus sign and then replace it with a direction. So it's 9 times 10 to the 9 downward, or south. Okay, that's all there is. Thank you very much.